Hello everyone, I am Sakshi from MSc Chemistry first year. Today I am going to read Physical Chemistry Unit 2 Thermodynamics. Introduction to Law of Thermodynamics. First law of thermodynamics states that the energy can neither be created nor be destroyed but can be converted from one form to another. The energy of an isolated system is always constant, which means that whenever some energy disappears from the system and equal amount of energy in some other form is also produced. Mathematically, we can say that W is directly proportional to Q, or W is equals to J into Q, where J represents the proportionality constant and is called Joule's mechanical equivalent of heat. The mathematical formulation of the first law of thermodynamics can be obtained from the increase in the internal energy of the system. The internal energy of the system can be increased into two ways. One is doing work on the system, and the second one is involves the supply of heat. Suppose that the initial internal energy of the system is even after supplying heat Q and doing work W on the system. The final amount of internal energy B E2 is equals to E1 plus Q plus W. E2 is equals to E1 is equals to Q plus W. Del is equals to Q plus W. Q is equals to del E minus W. If the work is done by the system, putting W is equals to minus P del V in equation 5. Q is equals to minus del E minus P del V. Q is equals to del E plus P del V. The physical significance of equation 7 is that heat absorbed by a given system is converted work done by the system and to raise its internal energy. It is also worthy to note that the general form of the first law of thermodynamics also applicable only in the case of chemical thermodynamics or physical process. In 1905, Albert Einstein showed that the mass can be converted into energy and energy can be back converted into mass. So mathematically, E is equals to mc square, where m is the mass and c is the velocity of light. Second law of thermodynamics. The second law of thermodynamics states that it is impossible to convert the heat completely into work without leaving some effect elsewhere. The second law of thermodynamics is actually a rational solution to the limitation of first law. In 1824, a French chemist, Sadi Carnot, showed that every heat engine there is an upper limit to the efficiency of conversion of heat to work. Let Q2 be the heat absorbed by the heat engine at temperature Tw, and W is the amount of work done by the system, while Q is the heat returned to the sink at temperature T1. Then N is equals to W by Q2 is equals to Q2 minus Q1 by Q2 is equals to T2 minus T1 by T2, where N is the efficiency of the heat engine is always less than 1, means that a heat engine can convert 100% of the heat and absorbed in the work. One more limitation of first law of thermodynamics is that it does not tell about the feasibility of the process. It simply talks if the heat gained or heat lost, but not the direction of the process. The second law of thermodynamics states that all the spontaneous processes are thermodynamically irreversible. The word spontaneous simply means a process that occurs by itself and external drivers is required. The second law of thermodynamics also states that the combined energy of the system and surrounding remain constant in ideal cases where the system is undergoing a reversible process. Law of mass action and its thermodynamic derivation. According to the law of mass of action, the rate of chemical reaction is directly proportional to the product of activities, or simply the active mass of the reactant is termed raised to its geometric coefficient. The law of mass of action can be used to study the composition of mixture in a reversible reaction under equilibrium condition. Consider a typical reversible reaction: A plus B equilibrium state, C plus D. Now from the law of mass of action we know that the rate of forward reaction Rf and rate of backward reaction Rb will Rf is equals to Kf A to the power A B to the power B. Rb is equals to KBC to the power C and D to the power D, where Kf and Kb are rate constant for the forward and backward reaction after equilibrium is reached. Rf is equals to Rb. Kf A to the power A B to the power B is equals to Kb C to the power C D to the power D. Kf by Kb is equals to C raised to power C D raised to power D by A raised to power A and B raised to power B. K is equals to C raised to power C D raised to power D, A raised to power A, B raised to power B, where Kf by Kb is equals to K. Thermodynamic derivation of law of mass action using equation 1 as AA plus BB in equilibrium state Cc plus Td. Now as we know that the free energy of reaction Gr can be and product Gp can be Gr is equals to A Ua plus B Ub. Gp is equals to C Uc plus Dud. Keep temperature and pressure constant. The free energy change of the whole reaction can be obtained by subtracting equation 8 from equation 9. Del G reaction is equals to Gp minus Gr. Del G reaction is equals to Cuc plus Dud minus Aua plus Bub. As the free energy change at equilibrium is 0, equation 11 is reduced to Cuc plus Dud minus Aua plus Bub is equals to 0. Now recall the expression of chemical potential of the nth species in gas phase, that is Ui is equals to Ui plus RT ln Pi, where Pi and Ui naught are the partial pressure and standard chemical potential of the species. Now equation 13 is in equation 12. C into U naught C plus RT ln Pc plus D into UD naught plus RT ln PD minus A U naught A plus RT ln Pa plus B into U naught B plus RT ln Pb is equals to 0. Or Cu naught C plus C RT ln Pc plus D UD naught plus DRT ln PD minus A naught minus ART ln Pa minus B U naught B minus B RT ln B RT ln Pb is equals to 0. Cu naught C plus C RT ln Pc plus Du naught D plus RT ln Pd minus Au naught A minus RT ln Pa minus Bu naught B minus RT ln Pb is equals to 0. RT ln Pcc plus RT ln Pdd minus RT ln Paa minus RT ln Pbb is equals to minus Cu naught C minus Du naught D plus Au naught A plus Bu naught B, or RT ln PCCBDD minus RT ln PAA PBB is equals to minus bracket Cu naught C plus Du naught D minus Au naught A minus Bu naught B RT ln PCCBDD by PAA PBB is equals to minus Gp naught minus Gr naught RT ln P C power C D P D power D P A power B P B power B is equals to del G naught reaction. Del G naught reaction can be simply abbreviated as del G naught. So equation 19b ln P C raised to power C P D raised to power D P A raised to power A P B raised to power B is equals to minus del G naught by RT. P C naught raised to power C, P D raised to power D, P A raised to power A, P B raised to power B is equals to epsilon raised to power minus del G by RT. Now because del G naught is a function of temperature only and R is constant quantity, the RHS can be put equal to constant Kp. Epsilon raised to power minus del G by RT is equals to Kp from equation 21 and 22. Kp is equals to PC raised to power C, Pd raised to power D by Pa raised to power A, Pb raised to power B, which is a more modern statement of law of mass of action, but in term of partial pressure. Other form of equation 23 can also be written depending upon the reactant and product involving. If the chemical potential of reactant and product are in mole fraction xi, Ui is equals to Ui naught plus RT ln xi, then equation 2 takes the form Kx is equals to xc raised to power C, xd raised to power D, xa raised to power A, xb raised to power B. Similarly, if the chemical potential of the reactant and product are in molar concentration Ci, Ui is equals to Ui naught plus RT ln Ci, then equation 23 take the form Kc is equals to Kc raised to power C, Kd raised to power D, A raised to power A, B raised to power B, which is a form of law of mass action. Third law of thermodynamics state that the entropy of system approaches a constant value as the temperature approaches a absolute zero. Mathematically, S is equals to 0 when T is equals to 0. At 0 Kelvin, the system is in a perfect order state, meaning all the atom or molecule occupy a fixed position in the crystal lattice. Since there is only one possible microstate, W is equals to 1, the entropy given by Boltzmann equation become S is equals to KL and W is equals to KL and 1 is equals to 0. As temperature increase from 0 Kelvin, vibrational motion begins and entropy increase. Note, valid only for perfect crystals. If defect is equals to residual entropy is greater than 0, absolute 0 cannot be reached in finite step. Provide a reference point for absolute entropy. Clausius-Clapeyron equation. The equation is useful in characterizing a discontinuous phase transition between two phases of a single constituent. Derivation of Clausius-Clapeyron equation considers a systematic equilibrium, that is, the free energy change for the ongoing process is 0. However, we know that the principle of thermodynamics states that the variation of free energy with temperature and pressure can be formulated by the differential equation dG is equals to V dP minus S dt. For the typical single constituent equilibria, phase 1 is equilibrium with phase 2, where phase 1 can be solid, liquid or gas, where phase 2 can be liquid or vapor depending upon the nature. Now consider a system at pressure P and temperature T, and the free energy are G1 and G2. Moreover, if we change the temperature from T and T to T plus dt and pressure from P plus dP, the free energy changes will be dG1 and dG2. So dG1 is equals to V1 dP minus S1 dt. dG2 is equals to V2 dP minus S2 dt, where V1 and S represent the molar volume of the entropy of phase 1, while V2 and S2 represent the molar volume and entropy of phase 2. However, if the phase 1 and phase 2 are in equilibrium with each other, del G is equals to 0, G2 minus G1 is equals to 0. Not recalling the fact that G1 and G2 are simply the free energies at temperature T and pressure P, we can say the same must also be true at temperature T plus dt and pressure P plus dP, that is, G2 plus dG2 minus G1 dG1 is equals to 0, G2 minus G1 plus dG2 plus dG1 is equals to 0. Since G2 minus G1 is equals to 0 from equation 6, so dG2 minus dG1 is equals to 0, dG2 is equals to dG1. After putting the values of dG1 and dG2 from equation 3 and 4 in equation 10, V2 dP minus S2 dt is equals to V1 dP minus S1 dt. V2 dP minus V1 dP is equals to S2 dt minus S1 dt. V2 minus V1 dP S2 minus S1 dt. Del V dP is equals to del S dt. dP by dt is equals to del S by del V. Now, if the del H is the latent of the phase transformation occurring at temperature, the entropy is del S is equals to del H by T. After using del S from equation 16 and equation 15, dP by dt is equals to del H by T del V. Now, if phase I is solid, where phase 1 is solid, where phase 2 is vapor, so equation 17 become dP by dt is equals to del fusion H by Tf del V. The term del V is equals to VL minus Vs. So equation 18 become dP by dt is equals to del fusion H by Tf VL minus Vs. For vaporization equilibrium, that is, liquid is equilibrium with vapor, dP by dt del vapor H by Tb Vv minus Vl. Now, since the volume of liquid is very small in comparison to the gaseous phase, the term Vl in equation 20 can simply be neglected. For simplicity, dP by dt is equals to del vapor H by Tvv. For if the vapor act as an ideal gas, that is, PVV is equals to RT or VV is equals to RT by P. So the above equation with dP by dt is equals to del vapor H by RT square into P 1 by P. dP by dt is equals to del vapor H by RT square dl and P by dt del vapor H by RT square. This equation is properly known as the Clausius-Clapeyron equation. One more popular form of Clausius-Clapeyron equation, which is derived from equation 24, dl and P is equals to del vapor H by RT square into dt. If the temperature changes from T1 and T2 and pressure is varied from P1 to P2, then integration of d ln p limit exists from p1 to p2 is equals to del vapor h by rt square into dt. Limitation exists from t1 to t2 ln p2 by p1 is equals to del vapor h by r t1 t2 1 by t square dt. ln p2 by p1 is equals to del vapor h by r t1 minus 1 by t1 minus 1 by t2. After converting to the common logarithm 2.303 log p2 by p1 is equals to del vapor h by r 1 by t1 minus 1 by t2 log p2 by p1 is equals to del vapor h by 2.303 r into 1 by t1 minus 1 by t2, which is integrated form of Clausius-Clipperton equation. Application of Clausius-Clipperton equation for transition between a gas and a condensed phase, liquid or solid. The Clausius-Clipperton equation can be given as ln p is equals to minus L by r into 1 by t plus c, where c is a constant, L is specific latent heat for a liquid gas transition. The boiling point of liquid at any temperature can be determined if the boiling point at a particular temperature and latent heat of vaporization of the same are known. If the latent heat of vaporization and vapor pressure of a liquid at a particular temperature are known, the vapor pressure of same liquid at any other temperature is known. Check if a phase transition will occur via compression or expansion in solid is equilibrium with melt equilibrium. Phase diagram for two completely miscible component system. As we know about Gibbs phase rule, F is equals to C minus P plus 2 for two component system. The equation 1 become F is equals to 2 minus P plus 2 is equals to 4 minus P. Type of two component system based on number of phases. First is when we use P is equals to 1 in equation 2, F is equals to 4 minus 1 is equals to 3. This means that for a one phase and two component system there are 3 degrees of freedom. This single phase can be gaseous, solid, solution or two completely miscible liquid. It is more common to vary only two variable while keeping the third one as constant. For instance, in case of pressure, temperature, composition is kept constant, while in case of pressure, composition, temperature is kept constant, while in case of temperature, composition, pressure is kept constant. When we use P is equals to 2 in equation 2, F is equals to 4 minus 2 is equals to 2. This means that for a two-phase system there are 2 degrees of freedom. These phases can be liquid, vapor, liquid or solid liquid. When we use P is equals to 3 in equation 2, F is equals to 4 minus 3 is equals to 1, which means that for a three-phase or and two component system there is only 1 degree of freedom. If the number of degree of freedom is only 1, there is only one variable that can be varied without distributing total number of phases at equilibrium state. If all the phases in two component system are either solid or liquid, only a minor pressure disturbance will have little to no effect on the system. So F dash is equals to C minus P plus 1, which is the reduced phase rule, where F dash is the total number of degree of freedom including pressure. Type of completely miscible two component system is solid liquid equilibrium. This completely miscible two component system can primarily be classified into three categories. Eutectic system. In this type of system the components do not react with each other, but only in the simple mixing take place in the solution or in the molten state. The common example of such system are lead silver system, bismuth cadmium system forming solid compound AXBY with congruent and incongruent melting point. In this type of system the components do not react with each other and the formation of a compound take place. The common example are Mn minus Zn system of Na2SO4 H2O system. This type of system can further be classified system forming solid compound with congruent melting point. In this type of system the two components react to give a compound which is a liquid which is quite stable and its melting point is reached. When melted the composition remains the same as that of the solid, and such compounds are said to have concurrent melting point. system forming solid compound with incongruent melting point. In this type of system, the two components react to give a compound which is not stable up to its melting point. When heated, the decomposition starts before the melting point is reached as a new solid phase and solution or melt with a different composition from the original solid form. Some of common example of such system: Na2SO4.H2 NaCl.H2 system. A regional phase diagram for system forming solid compound with incongruent melting point. System forming solid solution. In this type of system, the components are completely miscible with each other in solid phase and completely homogeneous solution are produced. The common example of such system are CONI system, AU-AG system, and AgCl-NaCl system. A regional phase diagram of system forming solid solution. Idiotic system. Calculation of idiotic system. It is obvious from phase diagram that the diagram has two curves OQ and OS enclosing the area ODS and SQE. The general phase diagram of idiotic system. The OQ and SQ curves. The point O and point S represent the freezing point, the pure compound A and compound B respectively. The curve OQ and SQ represent the temperature condition at which solid A and solid B are in equilibrium with liquid mixture. We need to reduce phase rule. So C2 is equals to and P is equals to F dash is equals to 2 minus 2 plus 1 is equals to 1, which means only one condition is needed to be defined to define the whole system. The curve OQ and SQ are called liquids because they separate the field of all liquid from that of liquid plus solid crystal. At point Q, all the three phases are in equilibrium with each other, and therefore 0 degree of freedom exists at this point. F dash is equals to 2 minus 3 plus 1 is equals to 0. This means that we can neither change temperature nor composition without disturbing the mutual equilibrium of solid B and liquid. Area ODQ and SQE. Area above OQS. It is obvious from the phase diagram that the area lying above the line OQS only has a liquid phase, means F dash is equals to 2 minus 1 plus 2 is equals to 2. Means we need to define both temperature as well as composition to define the system. Area below DQE. The area lying below line DQE has two solid phase, means F dash is equals to 2 minus 2 plus 1 is equals to 1. The only 1 degree of freedom means we only need to define the temperature to define the system. This curve is also called solid S because they separate the field of all solid from that of liquid plus solid. Area enclosed by ODQ. The area enclosed by ODQ line has solid A plus liquid phase, means F dash is equals to 2 minus 2 plus 1 is equals to 1. The only 1 degree of freedom means that we only need to define the temperature to define the system. Area enclosed by SQV. The area enclosed by SQV line has solid B plus liquid phase, means F dash is equals to 2 minus 2 plus 1 is equals to 1. The only 1 degree of freedom means that we only need to define the temperature to define the system. Cooling of liquid mixture and calculation of idiotic point rule. During equilibrium melting or crystallization in a closed system, the initial composition of the system will be identical to final composition of the system. Now consider the composition of the liquid mixture in which compound A is 80% while compound B is equals to 20%. Therefore, it follows the above mentioned rule that after crystallization we must get the same composition from figure A. Temperature T1. The composition X lies in the field of all liquid. However, when the temperature is reduced to T1 and crystal formation of A will be initiated, the further lowering of temperature will make more crystal of A to form. All this will result in a continuous change of composition of liquid mixture. Therefore, as a temperature is lowered from T1 to T2, the composition of liquid will change from point X to point Y. Likewise, lowering of temperature T2 plus to T3, then to idiotic temperature TE will change the composition from Y to Z and then to CE. By recalling the fact that all the three phases coexist at point Q, even an infinitesimal decrease to temperature will distribute the idiotic point and liquid will also start converting into solid phase. This will make the system move from point Q to Q dash, getting exactly the same composition X, that is 80% solid A plus 20% solid B. Calculation of atomic point. If the composition of the liquid mixture in which compound A is 80% while compound B is 28%, therefore it is follow the above rule. If the system allowed to cool down and then temperature is plotted against time, will get the cooling curve. The same system, since above point 1 the system is completely liquid, it will cool down very rapidly. However, point 1 the crystalline of compound A will also start releasing a large amount of heat there, and therefore rate of cooling will slow until point Q is reached. It is moving from Q to Q dash. The temperature of system will remain constant during the conversion. After point Q dash, both compound will exist as solid, and therefore the system will cool down below point Q dash. The same type of curve will obtain if we start from a composition left to the aquatic composition. The only difference will be that the compound B will separate out first up to point Q, and then the solidification of compound A will start. System forming solid compound AXBY with congruent and incongruent melting point. System forming solid compound AXBY with congruent melting point. In this system, the solid compound melt sharply at temperature T with same composition as in the initial solid. Consider two component AX and B, which also form a chemical compound AB by reacting with each other. Therefore, in the complete solid state, there will be a three-phase named solid, solid B, and solid AB. Curve OP and RS. The point O and point S represent the freezing point, the pure compound A and compound B. When compound AB is added to compound A, its freezing point decreases also along OP. Likewise, when component AB is added to component B, its freezing point decreases along SR. We show that the solid A and solid B are in equilibrium with liquid mixture. We need to reduce phase rule, putting C is equals to 2 and P is equals to 2. So F dash is equals to P 2 minus 2 plus 1 is equals to 1, which means that the system is univariate. In other words, only one condition is needed to define the whole system. Curve PQR. When compound A is increased in compound AB, its freezing point of decrease regularly along QP. Likewise, when compound B is added to compound AB, its freezing point decrease along QR. We need to use reduced phase rule, putting C is equals to 2 and P is equal to 2. So F dash is equals to 2 minus 2 plus 1 is equals to 1. However, it also to mention that at point Q also represent the congruent melting point of compound AB, because liquid and solid phase have the same composition. Third equating point P and R. In order to explain that the liquid phase can have two different compositions in equilibrium with solid phase, this makes the concept very simple, as the left and right part can be treated as simple equatic system. The right half of the diagram is equatic system with component B and AB, whereas left hand side is equatic system with component A and AB. System forming solid compound AXBY with incongruent melting point. In this type of system, the two components react to give a compound which is not stable up to its melting point. Consider two components A and B, which also form a chemical compound AB2 by reacting with each other. The cooling of all the mixture composition is carried out in open vessel so that the pressure remains constant. Point O, SQ and R. The point O and point S represent the freezing point of pure compound A and compound B. The point Q, however, is quite strange because it represents the transition temperature where compound AB2 decompose into compound B. The point R represents the hypothetical congruent melting point of compound AB. Curve OP, SQ and QP. OP is the fusion curve of compound A along which solid A is equilibrium with melt. The line SQ is fusion curve of compound B along which solid B is in equilibrium with melt. Similarly, QP is fusion curve of the compound AB2 along which solid AB2 is equilibrium with melt. The reduced phase rule gives F dash is equals to C minus P plus 1. F dash is equals to 2 minus 3 plus 1 is equals to 0, which means that there will be no degree of freedom at point P. Solid B plus solution that is in equilibrium with solid AB2. Therefore, in formation of compound AB2 will start, and since the three phases coexist at this point, the point Q also become invariant. Phase diagram. Thermodynamic treatment of solid solution. In this type of system, the components are completely miscible with each other in solid phase and completely homogeneous solid solution are produced. Generally, thermodynamic treatment of solid solution. The general thermodynamic treatment of solid solution include the shift in the solvent freezing point during the crystallization and nature of cooling curve as well. The shifting of solvent freezing point during crystallization. Let us assume the solid solution as an ideal solution. Therefore, the chemical potential of a ith constituent Ui can be Ui is equals to Ui star plus RT ln Xi, where Xi represents the fractional composition of the constituent, where Ui star is chemical potential of pure solid. After seeing the primary condition for the phase equilibrium between solid and liquid, U1S is equals to U1L. Consider both ideal. We can write above equation using equation 1. Ui star S plus RT ln X1 S is equals to U1 star L plus RT ln X1 into L. After arranging RT ln X1 S minus RT ln X1 L is equals to U I star L U1 star S RT ln X S minus ln X1 L is equals to U1 star L minus U1 star S ln X1 S by X1 L is equals to U1 star L minus U1 star S by T. The equation can be written as R ln X1 S by L1 L X1 L del fusion U1 by T, because U1 star L minus U1 star S represent molar free energy of fusion. Now putting the value of molar free energy of fusion in above equation, del fusion U1 star is equals to del fusion H star Im minus del fusion S1 star M. R ln X1 S by X1 L is equals to del fusion H1 star M minus del T del fusion S1 star M by T. R ln X1 S by X1 L is equals to del fusion H1 star M by T minus del fusion S1 star M. Recalling the entropy of fusion at temperature T1 star, del fusion S1 star M is equals to del fusion H1 star M by T. Using the above result in equation 9, R ln X1 S by X1 L is equals to del fusion H1 star M by T, del fusion H1 star M by T1 star. R ln X1 S by X1 L is equals to del fusion X1 star M 1 by T minus 1 by T star. R ln X1 S by X1 L is equals to del fusion X1 star M into T1 star minus T by T1 star. After putting T minus T1 star is equals to del TF in above equation, R ln X1 S X1 L is equals to del fusion X1 star M into minus del TF by T1 star. If the solution is very dilute, the melting point T1 star will be quite close to temperature T. Therefore, T1 star can be replaced by T1 star square. Therefore, equation 14 become R ln X1 S minus L n X1 L is equals to del fusion H1 star M into minus del TF by T1 star square. For very dilute solution, L nx1 into S is equals to L into 1 minus x2 into S is nearly equal to minus x2 S ln x2 L is equals to ln into 1 minus x2 L nearly equal to minus x2 L. Using equation 16, 17 in equation 15, R minus R into minus x2 S plus x2 L is equals to del fusion H1 star M into minus del TF by T1 del star square del minus del FTF is equals to RT1 del square by del fusion H1 star M into X2L minus S2S minus del TF is equals to RT1 square by del fusion H1 star M X2L into 1 minus X2S by X2L. Recalling the expression formularity X2L N2L N1L plus N2L nearly equal to N2L by N1L is equals to N2L by M1L by M1 is equals to N2L by M1 L into M1 is equals to small m capital M1. Using the above result in equation 20 minus del TF is equals to RT1 square T1 star square M1 by del fusion H1 star M into 1 minus X2S by X2L. Del TF is equals to minus KF M1 minus K, where K is the distribution constant given by X2S by X2L. The nature of cooling curve of solid solution now becoming, because the two components of solid solution are completely miscible with each other. Reduced phase rule is equals to F dash is equals to F C minus P plus 1. After putting C is equals to 2 and P is equals to 2, F dash is equals to 2 minus 2 plus 1 is equals to 1, which means that there is only one degree of freedom. In other words, only one variable is needed to define the system completely, which can either be temperature or composition. Further, there will be two breaks in the cooling curve, one at the start of the freezing of the solid solution and another at the end of the freezing of solid solution. After putting C is equals to 1 and P is equals to 2 in reduced phase rule, F dash is equals to 1 minus 2 plus 1 is equals to 0, which means that there is no degree of freedom. In other words, we will not able to change temperature or composition without distributing the state of equilibrium.